Let us discuss this example. Consider a set X A, B, C, D, E, and let Tor 1 be a set of X empty sets A, B, and A, B, C, D. This is an open set, this is an open set, this is an open set of A, B, C. Then Tor 2 is what? X empty set A, then C and D, A, C, E, and B, D, E. Then Tor 3 is X empty set A, A, B, A, C, D, A, B, C, D, A, B, C, D. Which of the following is a topology on X? We want to test that is it Tor 1 or Tor 2 or Tor 3 is a topology. So let us start. For us to show that Tor 1 is a topology, we have to test for Tor 1, we have to test for Tor 2, we have to test for 3. If and only if Tor 1 satisfies the 3 ratios in topology, we can consider Tor 1 is topology, and also in Tor 2 and Tor 3. Let us start from Tor 1. We have our set of X should be A, B, C, D, E. S is A, B, C, D, E. Then we have Tor 1 to be a set of X, 5, which is an empty set. Then we have A, and we have B, and we have A, B, C. So for us to satisfy Tor 1 as a topology, we must consider 3 issues. First issue is X an empty set belongs to Tor? Is our first issue in our previous class when I discussed on definition of topology. When we find that our X an empty set is a member of Tor, so it means a what? It means it satisfies the first issue. So let us consider issues 1. Issues 1, X an empty set must be a member of what? Topology. So we are considering topology 1. So that's why I have to be, it must be a member of topology 1. So if we go to topology, the set of Tor 1, we can find X an empty set here. So it means empty set is a what? Is empty set. Tor 1 included an element of X and empty set. It means issue 1 is satisfied. We have to test for issue 2. Issue 2 is what? To find the union set. We have to find the arbitrary union of the given set. Then Tor 3, the issue 3 is to find the finite intersection. Let's consider Tor 3. Issue 2. Issue 2 is to what? Issue 2 is to find the union intersection of this. If this we are considering Tor 1, we have to find the union intersection of this and this, then element of opposite of this. So let's consider our X and empty set. We are going to have S union empty set. S union empty set, it means the union means a common element, both elements that are present in given set. So S union empty set, we are going to have X. Can we find X here in our set of Tor 1? Yes, S is here. So S is a member of topology. Tor 1. So we consider the second union of set. We are going to consider A union B. A union B. So A union B is what? The element that is present in A, that is present in both elements. The element that is present in both. A union B, we are going to have A, B. A and B. So can we find A and B in Tor 1? Tor 1, we cannot find A and B and opposite of A and B. So it means since A and B is not a member of Tor 1, it means A and B is not a member of Tor 1. So A and B, A union B is what? A and B, and we cannot find A and B here. It means issue 2, A union B is not what? Since it is not a member of Tor 1, so it means it's not satisfied Tor 1. So we have to consider the next B and ABC. So we have to consider element of B, then union ABC. The union set of this, we are going to have ABC. ABC is a member of Tor 1. Can we find ABC here? Yes, we can find ABC here. So ABC is a member of what? Tor 1. So we have to consider the 3 issues. The third issues, we have to find the finite intersection of all this. S intersection empty set. When intersection means what? Common element between both sets. The element that is common. If we don't have element here, which is empty, and our X, since it is not common, we are going to have empty set. And we can find empty set here. So empty set is a member of what? Tor 1. So we have to try it for Tor 2. A intersection B. A intersection B is what? It's not common element. It's an empty set. Then we have to try it for what? B intersection ABC. Element that is common in both. B is here, B is here. So our B is here. Is B a member of Tor 1? Yes, B is a member of Tor 1. So it means we have done for what? We have tested for Tor 1. Since 1 failed to be a what? A union B failed to be a member of Tor 1. It means Tor 1 is not a topology. It's not a topology on X. On S. So let's go for Tor 2. Our first question for Tor 2. What do we have in Tor 2? We have X empty set A. Then we have X empty. We have A. We have AB. We have A. We have CD. We have ACE. And then we have what? BDE. So we want to find, we want to satisfy, we want to what? We want to justify our claim by looking at the three equations. Does it satisfy this Tor 2? If it satisfies, it's a member of what? Tor 2. So let's consider for first equation. Equation 1 is X and empty set must be members of topology. So we can find X here and empty set here is included. So to satisfy a members of what? Tor 2. So we consider the second one. Equation 2. We consider equation 2 the union set. X union empty set. We are going to have what? X is a member of Tor 2. We can find it here. We are going to find, we have to consider S this, and we are going to consider this. A union C and D. A union C and D. So we are going to have what? ACD. A union C and D. We are going to have ACD. A union C and D. We are going to have ACD. The element that is present in both. Element that are present in both A and CD. Can we find ACD here? No, we cannot find ACD in Tor 2. So ACD is not a member of what? Tor 2. We will go for what? CD and ACE. CD union ACE. CD union ACE. We are going to have AC, ACDE, ACDE, ACDE. So since ACD is not members of what? Tor 2. So it means ACD does not belong to what? Tor 2. So we are going to consider ACE and BDE. If you find ACE and BDE, we are going to have what? ABCDE. And ABCDE is not a member of what? Does not belong to this. Since ACE and BDE does not belong to this, equation 2 is not satisfied. Since one has failed, it means since one has failed, equation 2 has failed, it means equation 3. If equation 3 is satisfied, it means Tor 2 is not a topology. So if you consider equation 3, S intersection empty set, we are going to have what? Empty set. I'm going to have empty set is a member of Tor 2. Empty set is here. If you consider S intersection, A intersection is CD, A intersection CD, I'm going to have empty set also. So empty set. If you consider also this, we are going to have empty set. If you consider CD, if you consider ACD and ACE, you consider CD intersection ACE. Element that is present in both C and D, we have only C here. Is C a member of what? So C is not a member of what? Topology 2. They can find C here, but C is not staying alone. So that is why C is not a member of Tor 2. So let us consider ACE intersection BDE. So AC intersection BDE, element that is present here, that is also present here, ACE. So E is here. E is a common element among them. E is not a member of Tor 2. So it means Tor 2 is not a topology. Tor 2 is not a topology on X. Because some equations fail to be satisfied. In equation 2, A union ACD is ACD, and ACD is not present in Tor 2, so it's not a topology. So let's Test for third 3. Our third 3 is X empty set A and B, ACD, and ABCD. So our first axiom is X and empty set is the members of what? Third 1. X here, empty set is here, so it's the members of third 1. Our second axiom is the union intersection. So we have to consider the S union this. S union empty set. We are going to have what? X is the members of what? Third 3. We are considering third 3 to be in third 3. So we are now find A and B. A union AB. A union AB, we are going to have what? AB. The element that are both present. Element that are what? In A as well as in B. AB. So AB. Can we find AB here? Yes. AB is the members of third 3. Then we now consider AB and ACD. AB union ACD. If we consider AB union ACD, we are going to have both elements together. We are going to have A, B, C, D. Can we find A, B, C, D? Yes, we can find open subset A, B, and C, D here. A, B is the member of third 3. So we now consider ACD and ABCD. ACD union ABCD. So if you find the union of this element that is present, that is element, common element that is here, that is present here, everything. So we are going to have A, B, C, and D as well. A, B, C, and D. Can we find A, B, and C, and D? Yes, we can find it in what? Third 3. A, B, C is the members of what? Third 3. Then our last axiom is to find the finite intersection. Finite intersection. So we have to consider the finite intersection of this. S intersection empty set. We are going to have what? Empty set. Is empty set present in third 3? Yes. It's the members of what? Third 3. So we have to consider A intersection AB. A intersection AB. Element that is common here. Common element between them is what? A. Can we find A in third 3? Yes, we can find A in third 3. So A is a members of what? Topology 3. So we have to consider what? We have taken A and AB. We consider AB and what? AB intersection ACD. AB intersection ACD. Element that is common. Element which is common element is A. So A is common between A is a members of what? Third 3. So we now consider ACD and ABCD. ACD and intersection ABCD. The common element between ACD intersection ABCD. A is here, A is here, C is here, C is here, and D is here. D is here means ACD. The common element is ACD. Can we find an ACD here? Yes, we can find an ACD as open subset. It's the members of what? Third 3. It means our axiom 3, our third 3 is a what? Is a topology on X. That is, our third 3 is a what? A topology on S. The reason why third 3 is a topology on S is what? We consider the 3 axioms. It's the only third 3 that satisfies the 3 axioms of what? Topology. We satisfy that S and empty sets must be members of topology. We satisfy union of a set, arbitrary union of a set, which is axiom 2. The last axiom is what? Finite intersection. So in axiom third 3 satisfy the 3 axioms, and so third 3 is a what? Is a topology on X. So we have claimed that our third 3 is a what? Topology. Third 1 is not a topology because it's free. Third 2 is not a topology because it's free to satisfy the axioms. So therefore third 3 is a topology on X. Thanks for watching.